Okay, I think the meeting is getting recorded. Very good morning and very good evening, everybody who has joined in for today's session. This is Gokhale Jayanti, and I'm signing in from Mumbai, India. And I, along with Prakash, Prakash has signed in from Santa Clara. We are on, I think, session 16 or session 17. I'm not too very sure, but we are typically getting on with our series of sessions on quantum computing introduction. We call this as QC 101. And our emphasis right now is into quantum computing, the algorithms part of it. Right, the entire roadmap, which we started almost about 4 months back, typically started with quantum fundamentals, and right now we are at the quantum compute and quantum communication algorithms, right? So we are also getting introduced to these topics bit by bit, and also we are trying to showcase a few of these implementations using IBM Qiskit. So that has been our motive. And for today's session, we'll be talking about Blocksphere. So I'll be talking about Blocksphere for the first part of the session, and Prakash will pitch in, and then he will talk about what is meant by the QPE, the quantum phase estimation. Now, the Blockshere concept is something which we have already encountered much earlier. So, this will be a reinforcement of the same concept, number one. And then we will get into a little more nitty gritties as to how uh, any universal operation, right? We understand that most of these quantum operations are implemented as rotations, and we can typically talk about defining one gate, which is a bundle of maybe three rotations, and these can be used to implement any type of a small transformation, right? So we will try to define that also as well, right? So we will once again revisit this concept of Blocksphere, and then we will understand what is the concept of the expected value, and we will define this arbitrary single qubit matrix. We call this as the U matrix, and the U matrix is also directly made available as a function in the Qiskit library as well. And I'll show a bunch of some elementary Blocksphere illustrations also. And post that, Prakash will get on to what is meant by QPE. He's once again going to talk about this extension of this, and then he will discuss the concept of a controlled unitary gate. Right? So controlled U3 gate, as we also call it. Okay. So let me get started with this topic. Uh, we are all aware, actually, the moment we talk about picking up any single qubit, it is defined in the C2 space, right? And what is that C2 space? It is a two-dimensional complex space, and that defines the state of any qubit as a linear combination of the so-called basis states, the ket0 and the ket1, right? So we know about that. And what do you mean by this linear combination? So typically it is supposed to be having some coefficients, and these coefficients are also complex in nature. So I can now represent this state, which is phi, as equal to alpha ket0 plus beta ket1, where alpha and beta are complex numbers, right? So what do you mean by these complex numbers? So if at all I can just define these complex coefficients, it is as good as saying the fact that yes, I have got a complete control over defining the state of the qubit. And because these are two real numbers, technically speaking, these two real numbers can be specified either with respect to the real and the complex components, or we can represent that in the so-called polar coordinate form. So the moment we talk about the so-called polar coordinate form or the spherical coordinate form, when we come down to the overall representation, it comes down to the following. So I can just say that alpha is just nothing but some alpha magnitude constant multiplied by e raised to the power of I delta alpha. So that is some sort of an angle alpha. And similarly, beta can be also represented by e raised to the power I delta beta. Just notice the fact that alpha and beta out over here can be thought of as some sort of real number quantities. Similarly, delta alpha and delta beta are also some real number quantities. So primarily, we have got four values through which the state can be described. So people call this also as 4 degrees of freedom of an expression of the qubit state. Now, having said that, remember the moment we talk about a qubit, we also identify the fact that these coefficients have to be normalized because we talk about a unitary type of a behavior, and that puts in a small constraint to the fact that alpha square plus beta square will be equal to 1. So when I say that alpha square plus beta square is equal to 1, if I know alpha, I can estimate what is my beta. So which also means the fact that instead of these four real numbers that are required, I can now do away with one of them because alpha can be expressed in terms of beta and vice versa. I require now only three parameters to describe. So we say that okay, 1 degree of freedom is eliminated out, and then I require only 3 degrees of freedom to express this qubit state, right? So that is the fundamental thing. So the moment you just move a little forward in towards that, what we can say is something like this. So remember this uh, alpha and the beta parameters together will have to be equal to 1 in the context of normalized values. So I can just say that this alpha magnitude can be equal to some cos theta by 2, and beta magnitude is also now equal to sin theta by 2, simply because uh, we know that cos square theta plus sin square theta will be equal to 1, or in other terms, cos square theta by 2 plus sin square theta by 2 will also be equal to 1. So that is exactly what I was typically trying to mention. So the moment you plug that into defining the state of any qubit, so I can just say maybe psi equals to alpha ket 0 plus beta ket 1. If at all I just plug in these particular values, it boils down to a very, very simple representation. I'm not getting into the details, but if you just plug this in, you can just bring it down and then identify the following things. You have one constant coefficient that is coming up here. That constant coefficient is called as e I to the power of delta alpha plus delta beta, or maybe it's something like alpha plus beta. These are the two angles, let us say. Now notice the fact that this value, something like a constant value, is getting applied to both the cos component and the sine component, right? So this value is called as a phase. It contributes to the phase, and that particular phase is now called as a global phase. Now this global phase is a value there, but it does not really have any impact on the overall state representation of the uh, of our qubit. So that is the reason why we normally take it out. Really, typically do not consider it because it is not going to contribute much. Then this guy is going to apply itself to both the components. The so-called when you put it up into the bracket notation, it gets impacted or affected into the brass side as well as the ket side. Obviously, when it applies to brass side and the ket side, it gets applied in context with their complex conjugates, right? So that is not going to really influence majorly. So what I can do is I can just replace this value by some value equal to gamma, and similarly this the parameter like delta beta minus delta alpha can now also be represented by some other parameter called as phi. Now remember, we already have got the theta value here known, so I have got now these three parameters using which I can define this entire psi. Okay. Secondly, what exactly now is the major contribution? As I told you, e raised to the power of I gamma is not really going to influence anything. So this is called the global phase. And if at all I remove this global phase out, then I can very easily, without any loss of generality, I can say that this psi is just nothing but this combination. So it is cos theta by 2, the inner one, whatever is there, into e raised to the power of minus I phi by 2, operating on ket 0. This is a cos component. On a similar lines, it is e raised to the power of I phi by 2. Please understand, this is a sine component that is operating on e raised to the power of I phi by 2. It's something like a complex conjugate. And that is operating on ket 1. So this will be our fundamental equation which we are going to be using, indicating the fact that my single qubit can now be expressed only by two parameters, the theta and the phi. So we started with 4 degrees of freedom. It boiled down to 3 degrees of freedom, and now identifying this global phase, which is or getting applied onto both the ket side and the brass side, on both the ket 0 and the ket 1 components. We take it out, and the moment we take it out, we are just left with only 2 degrees of freedom, theta and phi. And the moment I have got this, what we can do is something like this. This theta and phi can be now used to represent the state on a sphere, and this particular unit sphere per se is called a Bloch sphere. So what is this Bloch sphere? Given any particular, let us say, I should say, the state defined by psi out over here, this is on the surface of the Bloch sphere. This is something like a vector, and that can be projected down onto maybe the so-called plane, and this particular plane out over here is just nothing but your xy plane, and onto that, the moment I project it, this is now going to subtend an angle equal to phi. Similarly, subtend an angle equal to theta along the so-called z axis and along the so-called x axis, right? So these two values, theta and phi, are good enough to describe the state of this particular point out over here on the Bloch sphere. So what are these theta and phi? These are just nothing but the polar angle and the azimuth angle. If you look at this into our normal spherical coordinate system, then we have this represented as polar angle and the azimuth angle. Right. So here is a small example. We know the fact that in this Bloch sphere, this axis is called the z-axis, pointing upwards, and that typically represents the ket 0, and exactly opposite end is identified as a ket 1. Okay, so this direction is the z direction, plus z is called as the ket 0, minus z is called as a ket 1. Now, along this axis, we call this as the so-called y-axis. This y-axis, we typically have this sort of a representation. You can normally call it as a sigma minus sigma, or you define it that way. More importantly, you have got this the x-axis that is coming out of the page, and that will be representing the so-called x-axis for a ket plus coming out, ket minus going in towards the page. Right? So this is something which we have already seen earlier on. And like last time, let us very quickly apply this. If at all I have a point right here, right on the top, we call this as the north pole, right? And the moment we consider this as a north pole, obviously now the value of theta will be equal to 0, and your phi will also be equal to 0, and you just plug in those two values. You can just say what is the state of the psi for theta equals to 0, phi is equal to 0. Just apply this will reduce down to ket 0. So we are right in defining this, indicating the fact that this ket 0, this particular point on the north pole of the Bloch sphere, indeed represents that. And if you do this similar type of an exercise for each of these north, south, east, west directions, you typically tend to get this representation for all the so-called 8 distinct points on the unit sphere. So this is the Bloch sphere. So here is another small example of the same thing. So if at all I look at this particular case, so I can typically define this extremes parameter in the Bloch sphere. So extrema essentially both define the minimum and the maximum value. And here I can identify this in the context of my polymatrix. And polymatrices are also now related to this. So once again, remember the fact that if at all I just use the same representation, psi equals to cos theta by 2 ket 0 plus e I phi sine theta by 2 ket 1, the moment I identify this particular parameter, please understand, this will be typically always going to be 1, irrespective of whatever is the value of this psi. So the moment I plug that in, notice the fact that the overall magnitude is only now determined by this particular angle theta, right? So by only this particular angle theta. And what exactly is the degrees of freedom for theta and phi? Theta can move from 0 to pi, so it can go from here down here, and phi can go 2 pi, so phi can just go a full circle out over here. So you have got this scope of the range for the values of theta and phi. Right, so this will allow me to define the so-called poly matrices also. Remember, we had the poly X, poly Y, and the poly Z, these three matrices which allow me to define the rotations along the X, Y, and the Z. So poly matrices also allow me to define the so-called rotation matrices R's. So here is another small example. So we talk in terms of this particular state, right? If I just consider this particular point out over here, once again the North Pole, and for the North Pole, we know theta is equal to 0, phi is equal to 0, like I did earlier on. If I just plug it in into these values, notice the fact that it boils down to uh, the final state to be equal to get 0. And a small demonstration of the same thing. If at all you look at the minus z axis, for minus z, theta is equal to pi. It has gone full half a circle down, so theta equals to pi, and phi still equals to be equal to 0. If at all I plug those values in here, this will boil down to psi equals to 8.1. Just to demonstrate the calculations are consistent. Second thing which we also now try to identify is this concept of an expectation values of any polymatrix, right? So what I mean by this polymatrix, remember the polymatrix is normally used to represent what exactly is the current energy level within that particular qubit state. And this energy level could be because of some sort of an external excitation which causes the state change to happen, right? So I can now define whether these energy levels have changed, increased or decreased, and that energy gain is what is very easily represented by the expectation values of the polymatrix. Okay, once again remember the fact that this is the basic equation which we are going to talk about. This is my basic equation for the overall state, and for any matrix M, I can identify the expectation value to be equal to this. Remember, this was my energy content. This is how we have defined that energy content also with respect to the eigenvalues, right? So this is my energy content, and the energy content is defined by performing both the Ket side and the Brass side operations. Now, when I take this value of e to the power of I sigma, remember I spoke about that earlier also. This e raised to the power of I gamma participates both on the Ket computations and the Bra computations. Obviously, remember it will be e raised to the power of I gamma and e raised to the power of minus I gamma. That is the complex conjugate, and they will eventually uh, combine together to be equal to 1 because it is a unitary operation. So the moment we know that, so the single qubit can now be once again defined by the same thing. We are just reiterating the same concept which I spoke earlier on. Now, what I can do is something like this. For some sort of a poly rotation, let's say like sigma z, I can estimate what is this expectation value, what is the typical energy level into that. So let me just quickly compute that out over here. It is once again extending the same logic out over here. So this is my basic starting equation, which I can now represent this in this column format. So remember this psi is equal to cos theta by 2 e raised to the power of something plus sin theta by 2 e raised to the power of something operating on ket 0 and ket 1 respectively. Both these two are complex conjugates. I can now represent that as a column structure. Having said that, if at all I want to now like to analyze this for, let us say, sigma z, the poly z, I just have to plug these values out over here, right? So what I'm doing is I'm just taking this entire thing as it is. This is my value and then multiplying that out over here. So I've got this phi out over here. Then I've got my sigma z, and then multiply by this. So this is my row matrix. This is my column matrix, right? So the moment I plug them out over here and then just go across, simplify that, it will boil down to equal to cos theta. Okay, so this is a cos square minus sin square theta. So we just use this simple trigonometric identity which says cos square x minus sin square x equals to cos 2x. So there is exactly what is plugged in out over here. Okay, so basically what does this mean? When you talk about the uh, expectation value of, let's say, one of the polymetrics, this is just nothing but a projection on a axis, a specific axis on the z axis out over here. So similarly, if at all you do the same exercise for poly x and poly y also, these stand out to become projections on the respective x and the y axes. So this is exactly how it typically boils down to. If at all you talk about this expectation value for poly x, this will work out to be equal to sine theta cos phi, and if at all you work it out for poly y, it will work out to sine theta sine phi. Okay, so this is what it basically means. So which also means the fact that expectation value is just nothing but the projection of that rotation matrix on the respective axes, right? X axis or y axis or even the z axis. So what we now define is something like this. Remember, whenever we talk about any unitary gate, that particular unitary gate is depicted as a rotation in the hyperspace, right? So what is this concept of this sort of hyperspace? So it depends upon whether you are inside of the sphere or outside of the sphere. So people look at it, okay, whether I'm inside of the sphere, are the rotations in the context of the sphere, or if I'm outside of the sphere, are these rotations now boiled down to into the context of the so-called my normal three-dimensional coordinate system. Now, the moment you talk about the three-dimensional coordinate system, this is your Euler space, the three-dimensional space, and out over here now you define the rotations. These rotations are called as the Euler's rotations, and these rotations are defined by the parameters theta, phi, and lambda. So these are the three angles through which the rotations can be described. So if at all you talk about any one qubit quantum gate, remember the one qubit quantum gate can be represented as a rotation on this one qubit quantum gate. It can be denoted as a 2 by 2 matrix, right? So this 2 by 2 matrix is a generalized representation for any gate that operates on one qubit. Right? We have seen that. So what is now defined is something like this. So we define a single qubit arbitrary unitary gate. We call this as a arbitrary unitary gate simply because using this I can implement any form of a rotation. And what I do is I define this as u, theta, phi, and lambda. So these are the three angles, and these angles are now specified in the context of my Euler space. Okay, so what is this unitary gate? The unitary gate is once again just nothing but the same representation what we had earlier on. So I just plug this in, it becomes cos theta by 2 into e minus I lambda sin theta by 2. Similarly, out over it will be e I phi sin theta by 2, the real component, and the imaginary component would be this. So you have got both the real components and the imaginary components correspondingly put up out there, and that will give you a 2 by 2 or 2 cross 2 matrix. Okay, so what basically is this? This matrix actually denotes a series of three rotations, right? A series of three rotations performed one after the other. First, you probably start off with a rotation around lambda. Then you start off with a rotation around theta. And once again, you get back to a rotation specified by the angle phi. And here the rotations are not across all the three specific axes, but the axes will be the z axis followed by, let us say, the y axis followed by once again the z axis. So you'll have three separate rotations. So this is what is actually now depicted here. So whatever are the rotations defined by the unitary matrix is identified as follows. So first and foremost thing is you rotate about the z axis by lambda. So that is the first rotation about the z axis. Then you rotate about the y-axis by theta, y-axis by theta. That's the second rotation. And the third rotation is once again a rotation by the z-axis by parameter phi. So these are the three sequence of rotations which you need to perform. And I'm just showing out over here in context the three-dimensional coordinate spaces out over here. And IBM Qiskit provides you with a function. This function earlier is popularly called as U3 gate, a universal gate. And now they have renamed that to call it as the U gate itself. So the U gate is available both in Composer as well as our Python library for implementation also. And the U gate typically takes these three major values and also defines or specifies which is that particular qubit on which the operation needs to be performed. So that is how the function is defined. We will talk about that also. Okay. So here there is once again the same thing that is going on. So we have got what is called as a an intrinsic rotation, as we call it, that is inside of the sphere. Now we are actually looking at what is called as an extrinsic rotation coming out, and then looking at the rotation from the context of the three-dimensional real space, and representation of these rotations are my Euler's rotation. Okay, so these are the three different names. So we also call them as alpha, beta, gamma. Here we call this as phi, theta, and psi. So please remember the rotation always will be z axis rotation followed by a y axis rotation followed by the z axis rotation. So we call this as z y z basis of sequence of rotations. And you normally specify by these three parameters of what exactly is the rotation: pi by 2, pi by 2, 0, pi 0, pi by 2, whatever. You can just specify those particular values depending upon which state now needs to be operated by what parameter. So that is your fundamental principle of your gate, the working of the gate. Okay. So as a small example out over here, we will see this one more time in detail. If at all I plug in theta equals to pi, phi equals to 0, and lambda equals to pi, this will work out to be equal to a u naught u gate, which is represented by pi 0 pi, and from a matrix point of view, it will work out to be equal to 0 1 1 0, which is just nothing but my u naught. Okay, so this can now be operated on ket 0, it will give you ket 1, and vice versa. If at all I operate this on ket 1, it will give me ket 0. Right? It basically causes ket 0 to be rotated down by 1 pi, pointing from upwards down to the south. And the moment I operate that, once again it rotates, continues in the rotation the same direction from the vector pointing south. It just rotates it down to rotates it up, sorry, pointing to the north. So let us see this in a little more detail. So how do I justify these actions? So I want to, let us say, construct a NOT gate using this universal representation. So what I do is something like this. So this is my generalized matrix for the U gate, and I know this is my NOT gate which I need to realize. So I just say that these two from the coefficients point of view should be identical. And if I just compare that, I'll typically get four equations. This cos theta by 2 will be equal to 0, minus e I lambda sine theta by 2 equals to 1. So that way I just will get these four equations, right? And just notice the fact that the moment I just plug in theta equals to pi, obviously these diagonal elements now will be made equal to 0. The moment I know that cos theta by 2 is equal to 0, theta obviously will be equal to pi. And the moment this cos theta is equal to 0, this parameter is also equal to 0. So it justifies that. So I can just say theta now equals to pi is what I need to define, number one. And if theta is equal to pi, then I can just say sine theta by 2 is equal to sine pi by 2, that is equal to 1. So this sine theta by 2 is now also redefined. So because of this, I can now say the fact that just plugging in these two values, right? So plugging into these values, I can now very clearly say the fact that my theta will be equal to pi, phi will be equal to 0, and once again lambda will be equal to pi. So just I'm plugging these values out over there into these four available equations, trying to realize what will be the values of lambda, theta, and together what will be the value of psi. So the three values are known. So I can now say the fact that the NOT gate can be now represented as the so-called universal arbitrary or unitary rotation matrix, and that unitary rotation matrix will have the parameters pi 0, pi. Okay. So from a rotation point of view, it is something like this. I first apply a rotation along the z-axis with a value equal to pi, followed by the second rotation along the let's say the y-axis, and that will be with angle theta equals to pi, and finally the third rotation will be equal to phi equal to 0. So let us very quickly try to visualize that. So this is a representation. We'll look at that when I get onto the small demo here. But let us understand this. Imagine you have got this a vector pointing to ket 0. So if at all I want to operate it on ket 0, obviously it should come down to pointing southwards. It should convert to ket 1. So let us apply the first rotation. The first rotation will be a rotation, right? Lambda equals to pi, right? So that is a rotation about this z-axis. So it doesn't really disturb anything. It doesn't bring in any change. Then the second rotation is a rotation by theta equals to pi. So this guy now zoop, it just comes down and then it now points downwards. So the north facing vector now will now become south facing vector after the second rotation. And the third rotation is once again about the same z-axis, phi equals to 0, and that will leave the vector unchanged. So after these three rotations, your vector pointing upwards to the north now pulls it down towards south. So that's how you have the operations to define the NOT operation. So we will look at that. And this is a small circuit. This particular circuit is demonstrating its operation. So this is my universal gate out over here, and it is operating on an input which is 0 and another input which is a 1. Now remember in IBM Qiskit, the composer more precisely, whenever you create a circuit, all the inputs will be initialized to ket 0. So if at all you want to get any input which is ket 1, we use the NOT gate out over here. I'm just defining a NOT gate to set up the input, and then I'm implementing another NOT gate using the universal gate or the unitary rotation matrix. Okay. Another small example out over here. This is showcasing for a Hadamard gate, right? The Hadamard gate is defined by 1, 1, 1, minus 1. So all of this factored with 1 over under root 2. We know about that. Just plug it in out over here. I just do not want to get into this thing. On a similar lines, just compare the coefficients and then knock it down. You will see the fact that this Hadamard gate typically works down to pi by 2, 0, pi. It works out to pi by 2, 0, pi. Okay, so we can just see that also in the demo a little later on. Another small example out over here I've got. Let us say you would like to implement this arbitrary state. Okay, so I just would like to implement this arbitrary state. So here, let's say I have psi equals to 1 over 2 ket 0 plus I root 3 by 2 ket 1. Now let us say this is an arbitrary state which I want to implement. It could be some point on the surface of the Bloch sphere, and it is neither the so-called ket 0 or directly ket 1. It is not pointing to any one of these so-called basis corner points. So this is a generalized state. So let us see whether this can be implemented or not. So the moment I look at this, I can find out how this entire thing transpires into pluggable values into my U3 gate. So let us work it out, a small exercise here. We know the fact that this is my general U3 gate that is represented, and given state can be put up into this particular column form. So the required psi is just nothing but 1 by 2 and I root 3 by 2. These are the two coefficients which I take and put them into the column form. So if at all I want to take this and then try to operate on, let us say, the state ket 0. So this will be multiplied with respect to state ket 0. Ket 0 once again has a column representation of this, and that will be equated to this value. And now all I have to do is what? Operate on this and then identify. So the moment I operate on this, this will reduce down to saying the fact that cos theta by 2, multiplied by 1 will be equal to 1 half. E I phi sin theta by 2, right, will be equal to I root 3 by 2. And I know cos theta by 2 is equal to 1 half, so I can evaluate sin theta by 2. And the moment I plug that value out over here, I can estimate this value of phi. So that is exactly what we are just doing that. So equating the individual elements, working backwards, I can plug these values and then I can get these values as phi equals to pi by 2 also. Okay, so what does this basically mean? My entire implementation could be equal to 2 pi by 3, pi by 2 and value equal to 0. Okay, so with this, there is a very simple exercise which tells me the fact that any arbitrary state can also be implemented using the universal rotation matrix or the U gate as we also call it. Another example, I would like to realize some sort of a matrix which corresponds to the rotation from ket 0 to ket 1. Ket 0 to ket 1. That is exactly what we have seen. So that is also represented typically by a NOT gate implementation. So let us say I just want to apply that out over here. Okay, so what is this application? One type of a realization is something like this. Remember, this is a NOT gate which we have seen earlier on. So what I will plug it in is from a slightly different context. The moment I want to rotate from ket 0 to ket 1, so this is something like a rotation about the y-axis, right? It's a rotation about the y-axis. Just imagine the rotation about the y-axis can also be thought about in the opposite direction as well. Okay, so the moment I say that it is purely a rotation about the y-axis without any other rotations along the x-axis and the z-axis, that also can be thought about in this particular form. And the moment I plug that in, I get a totally different matrix. This will still realize the so-called desired rotation, but please understand this is not a NOT gate, right? So please also understand the fact that you might be using alternate forms of a gate which might perform the operation but might not be the so-called standard, the so-called NOT gate or whatever gates which we know about, right? So that is also a small word of caution which you need to remember, and for that purpose only this small example was picked up out over here. So what we will now do is quickly I will just take you through a small demo sessions on IBM Qiskit, and I've just started my session here. And remember, I'm going to now pick up this unitary universal, sorry, not the unitary, it's a universal gate, and that universal gate is identified by the U matrix out over here. And this operates on one qubit, so I've created one circuit which contains one line for the quantum input, and this is my classical bit for my output in case I would like to measure. So this is my elementary implementation. So what I'm going to do is drag this U gate and plug it here. And the moment I have got the U gate plugged in here, it comes with a default set of values, which is pi by 2, pi by 2, pi by 2. Now I can just alter these values. And how do I alter that? Select this particular gate and click on this edit button here. And the moment I do that, I will get to alter these three values. Okay, so let me just implement a NOT gate. Remember, for a NOT gate, you have got the value should be equal to pi 0 pi. So let me have this pi 0 pi. I can do that here. Pi, I can just convert it to 0. It takes a little time there. So what I will do is I'll just go here to this editor. It just starts evaluating. Give me a minute, please. Oh, yeah, my Firefox is. So pi, I just edit that value here. 1 second. My machine suddenly slows down. Yeah, 0 and pi. Okay, so I just converted that. So it is a U gate which I specified here. A moment, please. I'm just resetting this. Okay, so pi 0 pi, easier to edit here. So the moment I have changed that, now this is now a standard inverter. Now just notice the input is a 0, and obviously because of this NOT gate operation, the output will be a 1. Input is 0 because that is a default input. So now you see that the output state is equal to a 1. And if at all I want to make my input equal to, let us say, a 1, the output now will translate to a 0. So this is actually implementing a NOT gate. And on similar lines, if at all I would like to showcase both these two operations, input is a 0 and input is a 1 simultaneously, if at all I would like to come up with some sort of entangled state, what I can do is create a circuit which has got 2 qubits, and I will just bring this second gate out over here, and maybe I can bring an identity gate here, and this also will have to be a NOT gate. So I'll quickly go back here and then edit the parameters. Okay, I'm just editing the parameters here. So I got this also as a NOT gate, and now just see my current state. Okay, so my state is, let us say, this is my most significant bit, remember. So it is 0, and this will be a 1. So input state is 0 1. So the flipped output state should be 1 and a 0. So 1 and a 0. And this is also what is depicted on the Q sphere. The Q sphere. I can just put up some measurements here and then bring it out. And obviously, even with my measurements, it will collapse down to observation of 1 0. So that sort of more or less completes my NOT gate. So if at all I would like to get a poly X gate, all I need to do is what? Typically plug in the values for the rotation. So I can just say that for a poly X gate, it will be equal to pi by 2. So I can just say pi and pi by 2. Okay, so let me just remove this. Currently, I don't need that part. I'll just will add the measurements. So I'm talking about, let us say, a single qubit implementation, one classical register, one quantum register, and this is my, let us say, the poly X. So what will happen with poly X? So my I remove this, my initial state will be pointing north, and after rotation it is pointing down south. The value will be equal to 1, and now see that the phase angle equal to pi. Phase angle is equal to pi, indicating the fact that my vector is pointing down. So this has become now ket1. Ket0 has become ket1. Similarly, drag one inverter here. So what will happen? Ket1, this is now ket1. Ket1 gets rotated down to become equal to ket0. So this is my poly X. And on similar lines, I can also bring in a Hadamard gate. Now for a Hadamard gate, the coefficients will be pi by 2, 0, pi. So let me quickly change it here only. Pi by 2 and 0 and a pi. Okay, so pi by 2, 0, pi. This gives me a Hadamard gate. And once again, I will remove this off. So this is behaving like a Hadamard gate with the input equal to 0. And obviously with an input equal to 0, it is putting this entire line into superposition. So you just see the um, amplitudes of 0.707, and if you look at the probabilities are equal to 50%. Very much similar to a normal standard Hadamard gate here. And for this is for the input 0. If at all I just bring in an inverter here, that will be for input 1, and for input 1 you know it is ket 0.707 ket 0 plus 0.707 ket 1 in with a negative. Fine. So this is exactly the output state also. Fine. And I can just bring in a measurement, and that will cause this entire system to collapse to one of the two values. So it has collapsed to this state. Fine. So this is basically a standard Hadamard gate also. Right. So I'll quickly show you the similar implementation also using Python. I'll just take about not more than 4 or 5 minutes. So this is a simple sample code. Similar thing you can also now implement and also visualize your Blockshere in Python. So I've got my standard imports out over here. So let me not get more into that. So what I will do is I'll just execute the cell as I explain as well. Okay, what has happened? Yeah, fine. Yeah, the cell got executed. Then I'm just adding the required imports for defining the quantum register, classical register, monitoring tools, NumPy, and then I'm also getting in basic air for my simulation purposes. So I'm going to execute this cell. Fine. And subsequent to that, I'm not actually pushing this onto my real device. So I just have commented this particular part of the code. If I push it, it will take almost a couple of hours before we can see the result. So I'm just using the air simulator itself. Fine. So I am now using this one backend, which is my Quasm simulator. So let me energize that. So that also is executed. And I want to display this block sphere, and for that you have got the visualization facility available through Qiskit. So I just say from Qiskit visualization import plot block multivector. So this block multivector can plot multiple states, right? So for example, the entire circuit can be displayed. If at all your circuit is a 3 qubit circuit, it will just display 3 Blockspheres, each Blocksphere depicting the state for one individual qubit. So that is what is your block multivector. And then once again, I'm just going to calculate the state. So these two imports are required. So let me bring them into context. Then I'm defining one quantum register and one classical register, each of them of 1 bit each, right? So, because these are 1 bit gates, I'm just only creating that. Having done that, I can now, by default, the moment you have created, remember what will be the inputs? The inputs will be zeros. Okay. So what I can do is I can just display this particular state. And to display the state, what I'll do is I'll extract the state of the system of the circuit. I can print it out, and then I can also plot the multi-state. So let me do the plot. Yeah. So it is displaying the state, and it is also now plotting the Blockshere. So this is my Blockshere, indicating the fact that this is a qubit pointing to 0. That is by default. Remember, if at all we don't uh, specifically modify, by default the inputs will be get 0. So that is my Blockshere pointing up. And then I can apply these gates. So how do I apply any specific gate? I have this U operator, which is the U3 gate, and then I specify all the 3 rotation angles, and I also specify the bit on which the operation is being carried out. Okay, so I can define this. So this is my, let us say, my circuit for, let's say, poly X, this is my value. For a NOT gate, this is my value. For a Hadamard gate, this is a value. For any arbitrary gate, remember the arbitrary gate which we saw in the example, so I can also plug that in out over here. So the ones values which you have calculated. So you define that particular circuit. So here I'm just going to define my U3 gate. And remember, if at all I want to make the input equal to 1, I will be adding that inverter also. This is my NOT gate. Right? So if at all I want to make the input line equal to 1, I normally bring in the NOT gate. So I've just commented that out just to indicate the fact that currently we are operating on an input which is equal to 0. So having said that, let me run this, and now you see the fact that that particular circuit is now defined, and I can now display the state, and that particular state is what is calculated out over here. Okay, you just see there is some component which is very, very small, e raised to the power of minus 17, this particular component, indicating the ket 0, and majorly it is very close to 1 for ket 1. So they indicating the fact that ket 0 got transformed to ket 1. And I can display the same thing using a plot mechanism. And now notice the fact that after the operation, now you see the Bloch block. The Bloch shows the fact that the qubit is now towards ket 1. And the same thing, I can do a measurement. Okay, and the circuit is getting printed. You can also print it this way, and I can also draw the circuit. Okay, that the same circuit is depicted here to visualize, and then I will just execute this. I am just running it to 8192, those many number of shots. I just run that. Okay, and what has happened? Yeah, and let me just see the counts which are obtained. So job has successfully run. Okay, and now I just print out this particular counts, and I should be getting all of them equal to 1. 8192. I'm running on the simulator, that's the reason. If at all I'm running on the actual device, probably I'll be getting about 8190 or 8185, very close to the full observed state of 1. Okay, so the same thing, if at all I want to bring in an inverter, all I can do is I can change the input out over here. Okay, so I just bring in an inverter. Let me just run this one more time, and once again I get the state vector. Okay, I have to reinitialize my circuit, start from here. Okay, start from here. I now bring in the inverter, followed by that will be my NOT gate. Okay, and that will now give me the fact that 1 operated by the inverter makes it equal to ket 0. So that is why you see this value equal to 1, and this value will be very, very small. So this is something like a small error that creeps in, and the same thing now can be depicted out over here. And now you see it is a vector pointing up. Initially it was a vector. What has happened? Okay. After applying the inverter, I did not display, but after my rotations, that ket 1 operated upon has now given me ket 0. And this is my circuit. Now you'll see the fact that there will be an inverter which will come in ahead of this. So this is my inverter and or the NOT gate, and the same thing in a pictorial representation is this. And I run this. Okay, I'm running it for 8192 shots, and now you will see the fact that instead of 1 as an output, I'll be getting 0 as an output with a higher degree of confidence, maybe all of them 8192 with a state equal to 0. So the concept is the same here. Now all you have to do is what? Change whatever circuit you want out of here. You can try for the Hadamard gate and stuff like that. Just comment this particular part, bring in that particular part for a Hadamard gate. Hadamard gate you want, you just comment this particular part, rating on input equal to 1, and that is how your Hadamard gate looks like. So if at all, give me one more minute, I'll just very quickly execute that. Okay, that is my original input. I'm now bringing in the Hadamard gate that comes in there, and I calculate the states here. Now you see that it is in superposition, so it is 0.707 get 0 minus 0.707 get 1. All right, 0.707 is 1 over root 2, and the same thing if at all I now display it in a Blockshere. Now that is my, sorry, it's not the Blockshere. Yeah, Blockshere. It is now showing up out over here. Okay, and that is my circuit depicted here. So this is my input, and this is my the universal rotation gate. And remember, even though it is a Hadamard gate is being implemented using U. So this is what my U will be. So for a Hadamard gate, you know, it will be U pi by 2, 0 and pi. And the moment I measure it, it will automatically collapse it to some value. Okay, so I'm running that on the back end. Job is successfully run. So let us see the status. So it shows me the fact that it is in perfect superposition, 0 for 4091 times and 1 for 4101 times. So pretty close to each other. Not exactly 50%, but pretty close to each other. Okay. So that is all I have got. Prakash?
Yeah, I'm there.
Yeah, Prakash.
Once
Yeah.
you stop sharing.
Yeah, I'll do that.
So what I'm going to do is share screen. So yeah, this is Google's.
Prakash, can I just
Yeah.
you can just get on to the basic concept, you know, the IBM Q implementation that I will show in the next session. I'll just take about 10 minutes to show that. I did not write the code for that. Okay.
Yeah. So what you are saying is IBM Q you will show
Next
next
time I'll
time.
show.
Okay.
Yeah.
So let me go to the where is the recording here? Okay. So let me view first. Let me what is that I wanted? Yeah. Okay. So let me continue on, folks. One sec. Where was I sharing? Yeah, here it is. So welcome everyone to the part 2. Part 1 was on the Blockshere. Part 2, I am trying to focus on what you call as quantum phase estimation. So till now we have ignored the phase. The problem we have been tackling is always on the magnitude, that is the expected value, and with the matrix. So this time we want to include phase estimation. Why? I will give you the reason, and then we'll go into general control unitary gate, which Gokhale already has presented. I will just uh, breeze through it, and then we'll leave the second implementation, which Gokhale said we'll take next time. So to start with, I will go back to what Gokhale had one common slide we had shared previously, saying that there is a difference between rigid body rotation, that is when you have a Q sphere with the axis included inside, and then you rotate it uh, clockwise. And that is the way it is generally if it is inside. That means if you rotate, the axis will rotate along and your vector will remain wherever it is. So you will only represent vector moving, whereas like if you have a clock and if your clock doesn't move, your circle moves in the clock, something like that. So the framework moving, which is internal, whereas intrinsic we call it. Whereas external, extrinsic or external means we are sitting out and we are rotating the vector, which is what we have been taking, which is counterclockwise. So our approach has been in QSphere as well as in our lessons, we always move the vector around counterclockwise. And the basis which we said the rotation will be ZYZ basis. And there was a question they all had put asking why is it that you are doing twice with respect to Z. Uh, so you remember the surface, the Blockshere is nothing but like a map. If you have a map and you are showing the map on, which is on a flat, and then pushing that onto a sphere, how will it look? Something you may observe, something you may not observe. Something is behind, something is forward. And Z, the polar axis. So whenever you do a polar angle, you have a polar angle we take with respect to Z, which is what we had done in the first exercise, first lesson, first time when we presented, we said that we have a polar and azimuth. So polar is your angle, which is with respect to Z, and that can go on X as well as Y. It doesn't prevent you from going X or Y, and therefore there are two rotations with respect to Z for both Y and Z, whereas for the Y, which is the representation of XY surface, there is only one, therefore one theta. So that's my explanation. Now you can give counter arguments, but to remember that we are representing a four, that is our dimension of freedom is 4 because we have 2. For a single qubit, we have got 2 alpha as I equal to alpha ket 0 plus beta ket 1, which amounts to alpha beta being complex numbers, and we are just taking alpha square, mod of alpha square and beta square equal to 1. So that means even though there are 4, we are representing 4 parameters, which is 2 real, 2 virtual, which is imaginary and real axis on a C2 complex space, and mapping that, like taking that and sticking onto a block sphere with the orientation going towards Z as the pole, not pole. And that's the reason you are going to have a difference. Um, Imagination is a little bit difficult, but at least you can imagine something. But if I say that I am rotating something, it doesn't mean the entire sphere is rotating, right? We are only talking of axis being rotated or the angle being rotated with respect to the axis for rotation. Therefore, you will never be able to say exactly this is what uh, there are many times when you have a knot available through different rotation, that it's after all rotation, whether I rotate x left or left, therefore there is a convention, and that is ZYZ axis. And we always take ZYZ because theta is the one which is in the middle, but represented in the gate as theta as first, whereas phi and lambda are pushed on the side. So you remember, even though we say ZYZ basis, the representation is always y, uy, and then you go into, but we don't say that. We say u theta phi lambda. And lambda is the one which is lambda and uh, phi are both with respect to z. So this we had done. I think I will just move on to the next one. So a single quantum qubit if you want to estimate, so we know that if you have we already did in the past something called a system. A qubit is itself a system, and if you have two qubits, they form two qubits, two systems. And when you mix up the two systems, then they have a mixed state. Whereas if it is a pure state, then it is single qubit. There is no interfere. There is no what you call effect of um, another qubit in the system. So this is a system. So the u theta phi lambda, even though theta is put, y portion is put here, z portions, which is the surface portions of phi rotation, lambda rotation, this equation remains same. And why theta by 2? There was one question, because the y rotation, the rotation, if you have a theta rotation is polar, and that polar is north pole to south pole, which is equal to pi, and therefore pi by 2 is the rotation, which is max. So, sorry, pi by 2 and pi. So 0 to pi by 2, it will come on the surface, 0 to pi by 2, another which will go into south pole. So if you start from north pole to south pole, you are going to go pi by 2 at a step. So the gate that are represented all, so this is the gate which represents all 1 qubit gates, but it ignores the global phase. So as long as it is a 1 qubit pure state, you can represent this. But if you have another qubit coming in and you are getting a mixed state because of the interference from one another and the impact of entanglement or superposition, whatever happens, that means you cannot use this. So you'll have to switch over. And that switch over means instead of having u theta phi lambda, we also add a term gamma, which is nothing but e raised to I gamma, which Gokhale had written as delta alpha plus delta gamma, sum of it equal to gamma. So it doesn't matter what you call it, it's a gamma, it's what is the other description of it. So when I say a qubit has a local phase, it has a global phase. So local, there is nothing, it is real, so nothing to worry about. When a global phase enters into the local space, then it becomes a mixed. And what is the impact of that is one thing. If you have two of them, then the question is you have to show the impact of this to describe the rotation. As long as they are unitary single qubit rotation, you don't have to worry. But when you get multiple qubits and you want to rotate, then you have to include the e raised to minus gamma, I gamma, e raised to I gamma factor. Now, e raised to I gamma factor, remember, it's imaginary. Okay. And another factor to that is this is global, not global, it is local global. There is one more factor which is global, which we ignore actually. That means what? There are many phases, but we only take local global for having combination of multiple qubits operation of rotation, and we always do only rotation, as we know, and that's what we get. So let's take a representation of a gate I00 minus I. If somebody asks me how do I represent I00 as a u theta phi lambda gamma, so this represents I00 minus I. So in this case, if you take I out and then multiply by 1, it is nothing, 100 minus 1. So this gate is nothing but I into something, and that something which is turns out to be Z or Z. So Z implies theta equal to 0, phi equal to 0, which is nothing, north pole, we had seen that, right? So we know that we can have Z factor here on this. So one of the possibilities, it is something like Z, but what else? So it also has a component I. So when you talk about I, then this is a um, so we have to talk about lambda factor first. So we spoke about theta and phi, we got it. So lambda factor is what we know is pi by 2 into n. So if you remember last time I had given some, so with respect to the phase factor, if we are only talking of real terms, then it goes to, because when you say phase factor in terms of 0 and 1s, because they are real numbers, here 0, 1, 0, minus 1. So only 1 and minus 1 are the two factors. 1, and so if I talk about lambda, the lambda and phi both are with respect to z, rotation around z. And if it is 0, 1, 0, minus 1, so in this case, lambda factor, I am taking it as 1, which is nothing, pi by 2 into 2. This is pi by 2 into 0, 1, 2, 3. Because we can go full circle. Full circle means pi by 2 into 4 we can go. And for first one it is 0, second one it is 1. So we have got a 1 factor here. So that means it is, what I mean by that is, we are getting a theta phi lambda. Lambda is equal to, in this case, turns out to be um, pi by 2. Am I right? Yeah, I think so. That's what we are getting here. And the last factor, no, sorry, we are getting pi here, because we are getting pi by 2 into 2, which is pi, and we are taking it as 1. Sorry, so lambda is getting as 1, and this is the formula for that, around z. And same around z for gamma will be based on the imaginary and real axis, as we had seen in the Q quantum Fourier transform. There it was 1 I minus I minus I. So if I go pi by 2 into, in this case it will be uh, pi by 2 into, we have to get a factor I, and that is, we are getting pi by 2 into 2, which is again pi in this case. So the pi factor will come here in the uh, sorry, pi by 2 into 1. So see, pi by 2 into, and I think I have some mistake here, because we have to go by uh, the angle. No, this is pi by 2 only. Sorry, it is pi by 2 only. There is some combination into 2. Pi by 2 into 2 is pi. And so I think I have some mix up here. One of them is going to be pi by 2, one of them is going to be pi. I'll fix this exactness, but the combination is 0, 1. This is real and this is imaginary. Imaginary will have a I component and real will have a 1 component. And that is why we are getting U00 pi by 2. 00 came by Z, pi came from alpha, gamma, and pi by 2 comes from the combination of, we need a I here, and that is equal to pi by 2. So the rotation, we can also verify that by using this u00 pi by 2, whether it is representing correctly by doing a multiplication, actual multiplication. And the difference between this and pi, so one has a pi, one has a pi by 2 extra because of the gamma factor. So lambda factor is here, but gamma factor is here. So if you apply gamma factor, then you get a I into alpha minus beta, because you can say I00 minus 1 into column vector alpha beta. You can say rho minus, this is a multiplication, this is the multiplication. So 2 by 2 into 2 by 1 will be 2 by 1 matrix, and that is 2 by 1, which is alpha minus beta with a I here. So what we say is, this universal gate with a gamma included gives a I with a minus I, whereas with just lambda, that is the difference between mixed state and uh, pure state, turns out to be only a difference of I. So when we use phase factor e raised to I gamma, e raised to I pi by 2, this is what? E raised to I pi by 2 is equal to I. Because you know that e raised to 0, e raised to pi by 2, e raised to pi by 4, 2 pi by 2, which is pi, 3 pi by 2, and finally 0. So this is e raised to I pi by 2, brings a I into this, and that's what I wanted to say, that rotated state vector are the same, except difference between phase factor of phi. So that's clearly the general control circuit gate. This I will have to verify. I may have some mistake here. I'll fix that later. But essentially you can see e raised to I pi by 2 is what matters, and that is the correct answer. So these are equation 3, 4, 5 for generally uh, controlled unitary gate. Now control unitary gate means we have to specifically say what is the 0 and the 1. What are you controlling? So if we write a general matrix for a controlled unitary gate, you saw arbitrary unitary gate Gokhale described. Now we are talking of controlled unitary gate. In the control unitary gate, if it is pure state, that is, if you have a 0 0 or a 0 1, nothing changes. Because controlling, what are you controlling with? You are controlling with a bit, and that is the MS bit. And if the MS bit is a 1, then you will have an impact. If MS bit is a 0, you will not. So if you look at it, you go a diagonal matrix. So let's say we always see that when we represent a gate, the columns represent the uh, unitary. So if I say 100 means I am looking at the first one. 010 means I am looking at the second one. If I have 4 by 4, there is, in this case we are talking about 4 by 4. So I'll have 00 and something, and 00 and something. You can see that these 4 are the ones which is the one complex one. So actually, if there was no complexity, it will come at 0, 100, 01, 0010, 100010, and 0001. That diagonally one unity matrix, which is what we need, unity. But for controlling, we will have these two which will be different, and that is what we need to be aware of. So if I say we want to define a controlled unitary gate, which means we are controlling the qubit in the basis vector is 0. It does nothing to target qubit. If the control bit is a 0, you will have no impact on the target. If control bit is a 1, then you will have an impact on the target by applying the unitary gate. So we can write the definition based on this as this. So you have 0, 0, 1, 1, 0, 1, 1. These are the two which are impacting. So when you have a mixed state of two qubits, these are not impacted because you have 0 zeros. But if you have a 1 here, then you have a unitary operation to be changed according to the gate theta phi lambda gamma which we had described previously. And that is what we are applying in both the cases. Otherwise, because of the control being made from 1 and 1 for a 2 qubit, we call it controlled unitary gate. We can talk generic, but to understand we have to at least show for 2. So we are saying that this is the combination. So simplifying, put it, control and unit gate, control and unit gate. For 0, what happens? For 1, what happens? So you have a ket 0 here and a ket 1 here, and then you can put the formula according to this, and then we can get the value out of it. This will turn out to be very much similar to this matrix with these two factors, and that is what is being done here. And another important thing is we have to call what is your input. So this depends on what is your input, right? This is a just a matrix. It's an operator. For operator to operate on a ket 0 or a ket 1, or in this case it will be kets, yeah, because we have got only, we are writing ket 00 is nothing but ket 0, ket 0, ket 0, ket 1. So basically we are operating on the second one, starting ms bit to ls bit. So the operation of ms bit on ls bit, when you take, so when I say E22, that means I am talking of element 2, 2. If I say 0, 1, 2, 3, because 0 to 3 is your 4 by 4 matrix. So it will be 2, 2. So when I take 2, 2 means 0, 0, 0, 1, 1, 0. So 1, 0. So you know that we can take the, what you call the matrix measurement, MPS, metric product state. we can determine by the ket 10, ket 10. That means 2 2. That is either you call it 2 2 or you call it 0 1 0 0 1 0 0 0 0 1 1 0. The second. So if you go by this, you are taking nothing but the value of that with a bra and a ket. And when you take a bra and a ket, we have done already the formulation. If you have bra 0 with a ket 0 with a bra 0, you just multiply and get 1. And you have a ket 0 with a bra 1, then you get this as 1. So basically the same thing can be applied to 1 0. Instead of 0 1, we can always combine this as 1 0 and 0 1, and that is what is being done here, to say that whatever your measured value of m which you want to get is only impacted by the gamma factor, which is the, otherwise it remains the same. So in this case, based on the previous what we have got, this formula, if you put the thetas and the alphas and theta 0 phi 0 and then a lambda and gamma, you get this cos theta by 2. And essentially this can be represented by ms bit to ls bit with a theta phi lambda on a unitary gate. So what is the importance of the equation? That is more important for us to understand. The equation says we should perform identity operation to the target qubit, because we are only interested in the phase. So the target qubit of the control 0 does nothing but with just the null operation, which is I operation. Otherwise it will be a control unitary operation. Now what that unitary gate is, that determines that. And in this case we will assume that it is only impacting the phase, and therefore we are only interested in the unitary phase. However, it could be a z operation, which is the standard for phase operation. So we can go with this and see what is the general circuit for 2 by 2 operation. So this was for 1 by 1 operation, which ms bit to unitary operation on the ls bit based on the control bit. That is, ms bit being 0, no impact, it's identity. If it is 1, there is a phase change. And this is because we are only interested in the phase portion, which is the global phase impacting the multi-qubit operation. This is a multi-qubit operation. Now similarly, if I go for another 2 by 2 matrix, I can just simply say that a circuit can be represented by, let's say that we are only talking of a E1, element 1, and the element 1 is 0, 1. Why am I talking of element 1? Because in a general qubit, we have phi equal to alpha 0 plus this one. And if I take a phase shift with a pi example, then we get this matrix, and which is nothing but a z. This is equivalent of z. So what I want to do is, phase shifting operation is with respect to a pi rotation with a z is what helps us in deriving what you call the measurement. What are we talking about? We are talking about the phase estimation. So what the phase estimation can be done is using a z operator, and that can be applied to a 0 or a 1. If you apply it to a 0, then you get 1. If you apply phase of phi shift, you get a minus. So basically this is the phase shift operation. So unitary phase shift operation applied on a pi, with a pi as the lambda, or pi as the gamma, is rotating and giving us a E0 and a E1. And so if the states are, they are called eigenvectors, so we call eigenvectors and eigenvalues corresponding. So if we take, our goal is to find this, there is a circuit which is rigged up here. So what we do is, we have a z which is the phase shift, and that we want to measure. And to measure this, we have two qubits, because we are now talking of 2 by 2 implementation. We did one one by one implementation, you are able to see that we have one with a control uh, of a unitary gate. Now with a 2 by 2, we have two qubits here, which is here in this case, don't confuse this with your classical registers. Here it is called a C register just for the sake of combining these two qubit. And the state, when you start, you give a 00 input, it is called as state is in psi 0. Then when you do a Hadamard, you get a psi 1, which is nothing but linear combination of these two. And then when you apply a Z, which is what we want to measure, so now the question is Z with respect to what? Z with respect to the middle one or the bottom one. Bottom one is MSB. So with respect to MS bit, and with respect to LS bit. And this is the least, but we have two registers, so B register. In C register, this is the MS bit, this is the LS bit. If we take entire, this is MS bit, this is middle bit, and this is the lowest bit. And in the least significant, LSB is what we have mounted our Z, because we want to measure the this quantum phase estimation is what we want to do. And the phase gate is always Z gate. So if you have, in this case, since we have got 2 to the power 2 qubits, 2 to the power 2, that means 4. So that means to measure, we will need to have first one as 2 to the power 0, second one 2 to the power 2, which is 2 to the power 3. So 3z, basically z into z into z, and here z into 1. So 1z and 3z we are applying on respective Hadamards, that is the psi 1, and then we are getting psi 2 by applying these two. So there is an equation to do this, and I'll share the equation, but explaining the circuit is much easier. So you got that. After this, if you do a quantum Fourier transform, we will be able to get the phase measurement. So the application of quantum phase estimation is first take a Z and then apply that with the Z, the phase which you want to measure with respect to the qubits, n qubits if it is 2. So we have got to know what is psi 0, psi 1, psi 2 and psi 3. If we do that, then our problem is solved. So what I will say is psi 0 is nothing, ket 0, ket 0 even. Why? Because we are taking the input as E1. Here you can see 0, 0 even when I am saying, that is because we took a path where we said that we are going to have a combination like we did here, E22. Here we are looking at a circuit where it has two registers called B register and C register. B register, as you saw, has Z input, Z gate, and because when you measure something, you need to have a exact eigenvector, eigenvalue as a input feed, then only you can measure. And in this case, we have taken, assumed that E1 is a column vector, which is 0, 1, which is nothing but pointing to the pole, North Pole, right? So we are taking 0, 1, E1 as the 1, which we are applying, and then our C register, which has got number of qubits, 2 to the power n. Since we have got 2 to the power n, we have got 4, and that means 2 to the 2 to the power 2. That means 2 qubits we are measuring. Now you remember that reversibility requires that we have equal number of inputs and outputs, and therefore in this circuit we have this B register is just like a ancillary type, or rather we are using the Z on this to measure what the phase impact will be on 2 qubits. So the 2 qubits are interacting and therefore they have a phase impact, and that phase impact can be measured using Z and then applying that and measuring on the MS bit in this case. And you remember why we are getting first, bringing first superposition, then applying the Z, the phase shifts, and the phase shift we said that PS, we said U PS phi, and that is what we are going to apply in general, and the phi we have taken as in this case as pi, right? So what we are doing is we are applying a phase shift of pi to each, and so therefore the application of pi for this will be 1, this will be 2 to the power minus 1, that means 1. So basically 2 to the power 2 minus 1 is 1, 2 to the power, so we are getting z to the power 2. So basically we are going to z square, z cube, z, whatever the number comes. As the qubits increase, we will have, but the effect of that is psi 0, psi 1, psi 2, what you measure, and then finally apply a QFT to get the output. Because why QFT? I will say because you remember that we had a 2 into pi um, into whatever the number of 2 to the 2 pi, like example we had taken n equal to 12. If we had 12, then we had to have m and the q. So if you had attended that m and q are the factors, we were defining that. Same way here, the 2n psi, because we have 2 qubit, 2 into n, and that is 4. N is equal to 2, so we have got 4 psi. Now we are measuring psi instead of 2 pi psi. So what we do is, instead of 2 pi psi measure, which is what we need to do, because we have to go by the imaginary real axis. Instead of 2 pi psi, we are trying to use a psi itself. So we are measuring psi instead of 2 pi psi, but that is why we will always, after that, we will apply the what a QFT to calculate. So in this case, psi 0 equal to ket 0 even. Our input is even, and therefore we are getting 2 qubits into even, and even is 0 1, and which is what we are applying here. So for this, the whole calculation is there. I am not getting into calculation, but remember, all we are trying to do is either a Hadamard to start with, followed by a identity, and then since it's a measured bra and ket notation with a even, it will turn out that you are getting 4 uh, combinations with even, which is the input. So input multiplied by half of ket 0001, this is what we are getting. And when you apply, this is a different position. So this is at the psi 1 position, we get this. At psi 2 position, we get, which is nothing but a matrix, which is based on the z. So how much z you are applying, z0, z1, z2, z3, how many you are applying, and that is what is nothing but a matrix notation. And at the psi 2, again we can review and revise with some kind of a combination of, to show that we want to get into e raised to I 2 pi. We apply that, and it turns out this is the equation. Won't get into too much of equation here, but finally what we are trying to do is, we have to apply for a phase estimation, we apply a QFT. And so the application of QFT is based on omega, which is imaginary. We had said m and 1 by root n of k0 to n minus 1 omega minus kj k, and that it has got implication of that on this. Without getting into detail, much more complexity, all I will say is sigma 3 is, sorry, no, psi 3, which is calculated as, because based on the normalization being 4, 2 qubit means we have 1 by 4 of this, k and j, they are just rotating out. Ultimately it is, whatever is in exponent comes to addition or subtraction. So if you remember, in the QFT we had said that if you have omega raised to whatever, in that case we had said k and qk, if q, uh, so the factor was either it should be constructive or destructive. If you get q equal to 0, okay, uh, then in that case we will get uh, interference, uh, q equal to, if we get a 0 in terms, we will get a constructive. And if you get a 1, which is like our, if you remember the Chronicle data we use, that if you have a dot product, and if they are same, if I say I dot I, that is bra I ket I, if I have a inner product, they are equal, then we get a value which is 1, because they are in the same direction. But if you get uh, they are in different orthonormal basis, then you get a 0. So that's the reason same thing is applied here for a constructive and destructive interference, interference, and then you end up in a So we had taken 1 0, if you remember, 0 0 0 1 1 0. We call it 2 or 1 0, it doesn't matter. So our k is what comes as the result. So actual result of this will be k, ket k. So whatever that ket k is nothing, but in this case we had said our input was k, which was 1 0, and therefore the phase of 1 0 is what we are measuring at the end of the day. And the same thing can be applicable for what you call general register, and you can do it with QPE circuit, and this is the what you call the phase estimation. So phase estimation is very important. Why it is important is because the magnitudes are always going to be unitary, whatever you do the operation. So then what's the use of the circuits? So the complexity that is involved in this phase estimation is very high, and this we are doing static at this time. And when you have millions of parallel operation and you have to do a dynamic estimation, that is the challenge one faces, and that's what is handled in the entire quantum, which is at a high advanced level. So at this time I should stop here because getting too complex. But what you take home is this: we can construct a general unitary gate with a control. So what Gokhale showed you was an arbitrary unitary gate. That means any gate can be represented by unitary gate, and our approach is to do a controlled unitary gate so that we will be able to estimate the phase. So quantum phase estimation is most important, especially when you are going to go into algorithms with larger depths. And even in the adiabatic, they call it, uh, they have to measure the phase, any algorithm for that matter. Phase estimation is one of the major important things. And Blocksphere can give you to certain extent only for a 3 dimension with maybe multiple qubits. But when you got in, of course it is limited qubits, but if you are getting into thousands and hundred thousands of or millions of qubits, and the depth goes 2000 types, width and depth of the circuits goes high for a high performance computing or for acceleration, then this QPE will come hunting. So better understand what is quantum Fourier transform, the imaginary real angular rotation, that is unity, what is called square root of or nth root of unity, and that is one which is used with the z. And so zy notation of uh, Blocksphere, which we saw, plus all this circuit development. How do you develop the, and most of the things are now moving on to Quasm 3.0, where they are trying to put it into unitary because they want to deal in volume, and therefore this becomes critical for us for advanced usage. Otherwise, you can ignore it. If you are not going into advanced, you are at the surface level. But those who want to do advanced will need to do this. So I think with that, I should stop sharing, and then hopefully, do you have any questions before I stop recording? Go ahead, Dhaval, Thomas, Gokhale. Anything commenting? Any comment?
Any comment? One small comment here. Now, this QPA becomes also very important when you want to encode your inputs. Now, for example, you're doing some image processing, or you're doing typically in, let's say, speech processing, or you're uh, setting up, let's say, machine learning module. Out there, those sort of algorithms really have to work out on the inputs. Especially if they have got large number of inputs, all you can do is just take the input, whatever it is. Different states of the input can be represented as phase representation, very much like the way we do it in communication, right? So you have got orthogonal phase division, modulation, etc. So those sort of techniques are there. Or quite on similar lines, QP is also one very interesting concept which allows you to also encode your inputs. I thought maybe I just have to mention that. Thank you.
Yeah, thanks, Gokhale. Actually, I had earlier assumed that it was quantum phase encoding, which is algorithm in itself, but the gates they were representing were for quantum phase encoding, and the encodings were Z basis, and the circuit is universal, can be applied anywhere. So it doesn't matter what qubits or unitary gate you apply to, Z gate is what is the key. How many Z gates? That depends on how many qubits you have, and obviously it is like a phase shifting has to occur accordingly. Example, if I have let's say 128 gates, 128 angles within that 360-degree, then I may be ending up with only 2 and 1.2 or 2.0625, some angle like that. So the angular rotation is very important, how much it is, and millions and millions when you do, then the phase becomes very, very smaller to distinguish. And that's the challenge one faces when you have subatomic particle. And this is important for hardware, maybe not for software. Software you can write as you please, because you are writing at the logical qubit level. But at the physical qubit level, the design of the gates impacts, and therefore this quantum phase estimation as well as quantum phase encoding is the challenge for a lot of people, and that affects the performance, that affects the optimization, and therefore that's key. And when we go to Shor's algorithm, we will see how we will handle QFT, which is the key for both the phase estimation as well as for the number crunching or factorization, as we say. So I think I will end it here unless Dhaval wants to say something after a long time. Go ahead. Dhaval. I think I'll assume we are ending the class here, and hopefully we'll see next time, next week. I know it's a tough, but we'll try to deliver on the last part of it. And if we need to extend maybe another for the final, but we see the 17 will be the last one, but we may extend to 18 as needed to close Gokhale. And I see that there is some need because he has already said he needs to show something, and based on shows maybe I'll be able to describe it, and then maybe we'll do post that the shorts representation. So maybe 2 more weeks max. Thanks everyone. I'll stop the recording.